for that.
Sorry, did you get me?
Send me an email. Sorry, I just put it away a moment ago. Once I put it away, I don't want to take it back out. All right, so here we are. Maybe I'll go over the schedule first. So I was almost done with 2.5 on continuity. I just have some problems at the end on the intermediate value theorem. Then I'll get started with 2.6. Okay, so I'll do 2.6 today and tomorrow. Tomorrow you get a quiz. The quiz would just be the same quiz I was going to give you last week. So it's going to be 2.1, 2.2, maybe stuff like that. It's just finding limits by plugging in, right? So I'll say find the limit as x approaches blah, 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 coming from the left and coming from the right, maybe. So you'll be plugging in stuff. And then from that list, you would say, okay, it looks like the limit is going to be 5, or the limit is negative 12, or whatever. Okay? So pretty straightforward quiz. Okay. Then I am going to mention something about next week, 2.7 and 2.8. I'm really treating it as one section. 2.7 and 2.8 is just one great big section as far as I'm concerned. Okay, the main topic is the derivative, using the definition of the derivative. Okay? And just so you know ahead of time, full disclosure of what it's all about, I'm going to show it to you right now, okay, so you can make a note of it. Now, if we were meeting face-to-face, I'd make you guys memorize this. Since we're not meeting face-to-face, you can put it on your cheat sheet. Okay, but the so-called definition of the derivative, it's on page 152. So make a note of this for later. I probably won't get to it this week, but just so you know. Okay, something called the derivative of a function. Okay, and here it is. Okay, see that F and that apostrophe? Okay, we read it as F prime. It means the derivative. So what is derivative? I've never heard of derivative. That's okay. This is what it means. F prime of x is equal to limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, now, in section 2.7 and also 2.8, you see lots of other definitions of the derivative. Okay, and I'm not sure why our author decided to give like 3 or 4 or 5 definitions. You can survive with just this one. So if you look at 2.7 and 2.8, you say, hey, the derivative also means this, and the derivative is this. They are equivalent. Okay, so it's not wrong. What Mr. Stewart has is not wrong. Who's Mr. Stewart? He's the author of the book. Okay, so it's technically not wrong, but I figured, why do you need 4 or 5 different definitions of the derivative? You can survive with just the one. Okay, so f prime of x is limit h approaches 0, f of x plus h minus f of x all over h. Okay, this is what you'll use for the derivative. Okay, so again, that apostrophe, you read it as prime. So like here, f prime, it means the derivative. Okay, now, as I mentioned before, some of you have had some background in calculus, and you already know derivative shortcuts. You cannot use any derivative shortcuts for this upcoming test. Okay, and I'll tell Prasanna right now. So Prasanna, if anybody asks you for help this week and next week coming for the test, and they say, I know derivative shortcuts, so Prasanna, you don't give them any derivative shortcuts. They must do it by this technique. Okay, chapter 3, we'll be learning all the derivative shortcuts, but for right now, if you have some background in calculus and you say, oh yeah, I know how to do derivative, I just do this, this, you can't do that. Okay, well, maybe I'll take it back a little bit. If you know shortcuts, maybe in the back of your mind, you can say, okay, if I did the shortcut, I'm expecting blah, blah, blah as the answer. Okay, so in your mind, you say, I'm expecting this, but then you still have to do all this stuff. Okay, and then if you end up getting what you expected by the shortcut, great. Okay, now, those of you who don't know any shortcuts, this is your first exposure to calculus, you're not handicapped in any form or fashion. We'll give you all the shortcuts when we get to chapter 3. But for right now, for me and for Prasanna, you must use this as a derivative. You cannot use any derivative shortcuts. Okay, maybe just as a double check in your mind, you say, okay, I'm expecting blah, blah, blah to be the answer. And then, hopefully you do get the answer. But if you have no calculus background, that's okay. Just use this for the formula for derivative. So we're going to use this thing all throughout 2.7 and 2.8, which is the main topic of next week. So next week, we're going to do derivatives, derivatives, and more derivatives. In fact, most of the rest of the semester, we're going to be doing derivatives, derivatives, and more derivatives. That F prime notation, F with the apostrophe. Okay. So again, I'm going to freely flow between 2.7 and 2.8. So in my mind, 2.7, 2.8 is really just one great big section. Okay, so I'll bounce back and forth between 2.7 and 2.8. It's one section on the derivative using the derivative definition. Limit h approaches 0, f of x plus h minus f of x all over h. You can put it on your cheat sheet. If we were meeting face to face, I'd make you guys memorize it, but I'm not making you do that for now. Okay? So that's what we're doing. All right, so let me get back to 2.5 now. The last topic was something called the intermediate value theorem. So let me show it to you and then do some problems with it. So these are the last problems, just 53 through 56. I was pretty much done with everything besides that. Okay, I think I give you everything that you need for that. But 53 to 56, where'd it go? There it is. Okay, so intermediate value theorem. It's on page 122. Here it is. Might be kind of hard to read. Suppose that f is continuous, key concept, continuous, no jumps, no gaps, no breaks, on a closed interval from a to b, and let n be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c between a and b, such that f of c equals n. And you say, huh? What are you talking about? Okay, so here's a picture. So here's a, here's b. A comma f of a, b comma f of b. It's a continuous function. See how it's continuous, right? Smooth, no jumps, no gaps. So what they're saying is let n be any number between f of a and f of b. Somewhere the function value attains n. This is what they're calling c in this picture. There exists a number c such that f of c is n. Okay, so n exists somewhere. It has to happen at least once. Now what they're showing you here is it could happen more than once. Okay, so here's f of a, f of b. In this particular case, if n is here, it touches 1, 2, 3 places, right? But it has to happen at least once within the interval. Okay, I think it's more intuitive if I give you actual numbers. Okay, so let's suppose this y value is 3 and this y value is 10. You don't have to write this down as long as you understand the concept. Okay, so let's say this is 3, this is 10. And it's a continuous function. That means you can graph it without lifting up your pencil from the paper, right? So pick any number between 3 and 10. 4, 5, 6, 7, 8, 9, 7.5. Pi is in there, right? 5.3165214148228. Okay. Somewhere between a and b, the y value is what I just said. 5.316521314, whatever I said. Okay. The x coordinate is what's considered n. Okay. So it's smooth. So if this is 3, this is 10, then somewhere between 3 and 10, okay, any number you pick, it's obtained on the graph. Okay. The x coordinate is what they call c. Now it can happen more than once, but it has to happen at least once. So all the numbers between 3 and 10, 4, 5, 6, 7, 8, 9, 9.5, 5.24, they're all in there. That's what they're saying here. Okay, now, in particular, as an example of this, how do we use it for the homework? Okay, suppose I have a comma f of a, b comma f of b. One of them is positive and one of them is negative. Okay, so this one's negative, this one's positive. They can be reversed. This one can be positive, this one can be negative. Okay, and it's a continuous function. Okay, so I'm going from here to here, and no jumps, no gaps. Then, do you agree? Somewhere we have to touch the x-axis. There's going to be a y coordinate of 0. If this is negative and this is positive, 0 is between any positive and negative number. So somewhere it has to cross. Right? They must connect. So this is just about as far as I can go. Right? And it's continuous. Okay? Now you can see if I made it discontinuous, then sure, you can jump and it doesn't touch the x-axis. That means y equals 0. But if you're insisting that it's continuous, then somewhere the y-coordinate is 0. We'll call it C. Right? That's what we're talking about. Now, it's allowed to happen more than once. In fact, it can happen a whole bunch of times. Okay, so let me show you the same picture. We can touch the x-axis a whole bunch of times and be a function, right? You can have fun with it and just kind of go like that, right? So you can touch a whole bunch of places, 1, 2, 3, 4, 5, 6, 7, or whatever. Okay, but if you have a continuous function, it has to touch the x-axis at least once. That means y equals 0. Okay. If you relax the restriction of a continuous function, if the function's not continuous, then certainly you don't have to touch the x-axis, right? So suppose I have a graph like this. We've seen instances like that, right? And then it joins up again over here, right? So if I do not insist on a continuous function, then sure, it's possible not to touch the x-axis. Okay, but if one point is positive, one point is negative, and continuous, then you have to touch the x-axis at least once. That means y is equal to 0. It can happen a whole bunch of times. But if it's continuous, it has to happen at least once. If it's discontinuous, then no. It's possible not to touch the x-axis. All right, so now what are they talking about in the homework? (126). Use the intermediate value theorem to show that there is a root of the given equation in a specified interval. Okay. What they're saying is that there's a solution somewhere in the interval that they're giving you. Okay. And the way to do that is, now 53 is tailor-made. It's already 0. You have to have a 0 on one side, either left or right. Okay. And if it isn't 0, like 54, 55, or 56, you make it 0. And that's easy to do. You just throw everything on one side and set it equal to 0. Okay. So I'll show you 54 and 56 because they're even, and you'll do 53 and 55. Okay. So here is 54. It's that ln x equals x minus radical x between 2 and 3. There's a solution somewhere between 2 and 3 is what they're saying. Okay. Now, what you have to do is have a 0 on either the left side or the right side. So I subtracted x and I added root x. Okay, so it looks like this. F of x equals ln x minus x plus radical x equals 0. Okay, so I moved x, that becomes a negative. I moved the negative radical, it becomes positive. Okay. Is this a continuous function? Well, we know logs are continuous, polynomials are continuous, square roots are continuous. If I add or subtract continuous functions, it's continuous. So yes, this is a continuous function. All right, so here's the strategy. All you do is plug in the two endpoints, show that one of them is positive and one of them is negative. It doesn't matter which is which. Okay, so f of 2. Okay, so I plug in 2 here and here and here. ln 2 minus 2 plus radical 2. Okay, punch it in the machine. I'll save time and just tell you what it came out to be. You can do it as well as I can. 0.107. F of 3. Plug in 3. ln 3 minus 3 plus radical 3. Punch it in the machine. Negative 0.169. Okay, and there we go. So here's a little mini picture. 2 comma 0.107, it's positive. 3 comma negative 0.169, it's negative. Okay, so here and here, it's a continuous function. So by the intermediate value theorem, okay, somewhere we have to cross the x-axis. That's what they call C. Okay, so f is continuous. Here, f of 2 is greater than 0. I made a mistake here. So this is the exact opposite of the picture I just showed you. This one, this side was negative, this side was positive, but in the one that I've got here, it's the other way around. This side is positive, this side is negative. That's okay. As long as one is positive and one is negative. F of 2 is greater than 0. That's a greater than sign. I messed up. F of 3 is less than 0. So the intermediate value theorem says there's a C between 2 and 3 such that f of C equals 0. If it's continuous, somewhere we have to touch the x-axis, which means y equals 0. So that's what they mean by root. There's a solution somewhere in there. So this is called the intermediate value theorem. And let's make an abbreviation, IVT, for intermediate value theorem. Okay, so intermediate value theorem, IVT. So that's all. So the strategy is put everything on one side, set it equal to 0, plug in the left endpoint, plug in the right endpoint, and just show that they're different signs, SIGN. Okay, so 56, sine x equals x squared minus x. Okay, the right-hand side is supposed to be 0. So the only one that's perfect, so to speak, is 53. It's already a 0. 54, 55, and 56, they aren't 0. So just make them 0. Just throw everything over to get a 0. Okay, so I messed up again here. So if I subtract x squared, it's like that. And if I add x, it's like that. So sine x minus x squared plus x equals 0. And by the way, sine should be which mode? It's radian mode right now, right? So if you aren't in radians, if you're in degrees, change it to radians when you're punching this one out. Okay, f is continuous. Trig functions are continuous. Polynomials are continuous, right? The sum and difference of continuous functions is continuous. So this function will be continuous. All right, so plug in 1. Sine of 1 minus 1 squared, that's minus 1 plus 1. That's a sine of 1. You can punch it in your calculator. It's going to be positive, greater than 0. I just know that's the case. Plug in 2. Sine of 2 minus 2 squared plus 2. That's minus 4 plus 2. Sine of 2 minus 2 is less than 0. And actually don't even need a calculator for that. Can you see how I can do this without a calculator? Although you're allowed to. Okay. Remember, sine only returns values between what two numbers? Sine of anything is between negative 1 and 1, right? So the biggest this can ever be is 1, but now you're subtracting 2. So no matter what number I have between negative 1 and 1, if I subtract 2, it's going to be negative. So there it is. One side is positive, one side is negative. So by the intermediate value theorem, okay, there's a C between 1 and 2 such that f of c equals 0. So you can have that very language. You can copy this as an example on your cheat sheet if you want that language. The language is there's a C in the open interval from 1 to 2 or between 1 and 2 such that f of c equals 0. Okay, so that's the intermediate value theorem. So there are only 4 problems like that. I did 54 and 56. You do 53 and 55, and now I'm done with this section. Okay, so here it is, intermediate value theorem. Okay, so once for the homework, one side's positive, one side's negative. Therefore, somewhere in the middle, you get a 0. Okay. All right, so I'm ready to start 2.6. Limits at infinity and horizontal asymptotes. Okay, so we've already done some infinity, but now we're going to take the limit as x approaches infinity or negative infinity. Okay, so this is page 126 and now 127. So I want you to look at the symbolism here. 127. Limit as x approaches infinity of f of x equals L. Okay, so that means you're plugging in bigger and bigger and bigger numbers. So if you were to actually make a table, right, and punch in stuff on your calculator, that means you're plugging in 100, 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000, and so on. Okay? And as you might guess, you can also have limit as x approaches negative infinity. Okay? So as x approaches infinity, you're going way out to the right. Limit as x approaches negative infinity, you're going way out to the left. So you would be plugging in negative 1,000, negative 1,000,000, negative 1,000,000,000, negative 1,000,000,000,000, and so on. Okay? So that's limit as x approaches either negative infinity or positive infinity, going forever to the right or forever to the left is what we're looking at. Okay, so in this case, limit as x approaches infinity of f of x equals L. So when x gets super big going to the right, y approaches L. And they're giving you 3 pictures here of the same thing. Okay, here it looks like we're coming from below. That's okay, we're getting really, really, really close from below. Here it looks like we're getting really, really close from above. Here it looks like you're just squiggling back and forth. Okay, we're still going to call that the limit as x approaches infinity is L. Okay, in each case, this is what's called a horizontal asymptote. Okay, I think you've heard asymptotes before. If you want the spelling of asymptote, here it is, YMPTOTE. Okay. I do want to emphasize one thing about asymptotes. You may have heard that an asymptote is a line that the graph gets real close to but doesn't touch. Okay. Don't have that doesn't touch business. That's not necessarily true. Okay. So it's a line that the graph approaches, period. Okay. A lot of the times it doesn't touch. And a lot of the examples that we've given you, the graph doesn't touch the asymptote. That's not technically true. So this is still considered an asymptote. We get really, really close to y equals L, but it does touch. Okay. So this is an example of a horizontal asymptote. We've seen vertical asymptotes. Now we have horizontal asymptotes. So take out the restriction that the graph does not touch the asymptote. A lot of times it doesn't, so sometimes students will make the conclusion, oh yeah, it looks like a lot of times it doesn't touch the asymptote, so that must be the definition. No. Okay. You are allowed to touch the asymptote, but a lot of times it doesn't. Okay. Okay, so on page 128, limit as x approaches negative infinity of f of x equals L. So again, you're going all the way out to the left. So here's a graph. If you go all the way out to the left, very large negative numbers, negative 1,000 you plug in negative 1,000,000, negative 1,000,000,000, then we get very close to a particular number. You could also approach from below, once again here, and again, take off the restriction that it doesn't touch. No, here we do touch. All right. All right, so we have a horizontal asymptote. If either limit as x approaches infinity of f of x equals L, or limit as x approaches negative infinity of f of x equals L, we have a horizontal asymptote. Okay, here's an example of a graph. It's a good idea to know something about this graph. And you say, do I have to memorize it? Well, you can put it on your cheat sheet, obviously. This graph is going to show up quite a bit. It's the inverse tangent function, right? And you're going to see a lot more of that in Calc 2 also. So it's good to have some idea of the inverse tangent function. It looks like this. So the limit as x approaches infinity of the inverse tangent function, limit as x approaches infinity of the inverse tangent function is pi over 2. So as x goes way out to the right, or if you plug in 1,000,000, 1,000,000,000, 1,000,000,000,000, okay, we get real close to pi over 2. Okay. The limit as x approaches negative infinity. If I plug in negative a super big number, right, way out there, then we approach negative pi over 2. Okay. That's what's happening there. And maybe just for fun, do I have time? Yeah, I'll go ahead and show you this. Okay, so I'll show you on my calculator. Okay, so I'm in radian mode, inverse tangent of a super big number. So I'm putting 1 and then a whole bunch of zeros. Sorry if I'm burning out your eyeballs there. 1.5707. And let me see by comparison, what is pi over 2? 1.57. Okay, so just for the calculator itself, you can't tell the difference. Every digit was correct. They're actually not quite correct, but you probably won't be able to tell until you go out to more digits. So I did inverse tangent of a super big number, pi over 2. And inverse tangent of a super big negative number from this graph. Whoops, where'd it go? Inverse tangent of a super big negative number, I should get negative pi over 2. So negative 1,000,000,000. Okay, so I did inverse tangent of negative 1,000,000,000. It was negative 1.57. In other words, negative pi over 2. So there you go. Okay. Now, there are certain functions where you should be able to come up with a limit fairly quickly. You don't need to plug in a bunch of points. Okay. Let's look at the graph of 1 over x again. Okay. Again, you should be somewhat familiar with 1 over x. Looks like that and like that. So what happens when x gets super big? Looks like y approaches 0. If I plug in 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000, right? You have 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000, 1 over 1,000,000,000,000. Okay, you don't need a calculator for that. That's almost nothing. Right, so you should be able to figure that out without punching in values. Likewise, limit as x approaches negative infinity. If I go way out here, the limit is also 0, but it's a small negative number. So look at this. If I plug in negative 100, negative 1,000, negative 1,000,000, negative 1,000,000,000, negative 1,000,000,000,000, you don't need a calculator for that. It's also very small. It's a very small negative, but it's still essentially 0. Okay, so you should be able to recognize that fairly quickly. Okay. And then over here, they're saying if you have 1 over x squared or 1 over x cubed or 1 over x to the 4th, okay, if you plug in super big numbers, it's still going to approach 0, right? Like 1 over x squared, 1 over x cubed. When x gets super big, it still approaches 0. Okay, so you should recognize that because after a while, we don't want to keep plugging in stuff. You should just know that an expression approaches 0 or an expression approaches infinity and so on. Okay. So let's get started. Okay, 3 through 10 is on our list. Let me take a look. Yeah, 3 through 10. So I'll start off with the even ones. Okay, 4 uses this picture, and I can't show you both at the same time, so I will just read this when we get to it. Sorry about that. Okay, so I'll read these, but we're looking at this. Okay, so 4a says limit as x approaches infinity. So as x approaches infinity, we go way out here. The y values are close to 2. Okay? And again, there's no law that says you can't touch the asymptote. Okay? So the answer to A is 2. B, limit as x approaches negative infinity. So I go way out that way, and it looks like the y values are at negative 1. So the answer to B is negative 1. C, limit as x approaches 0. And it's two-sided. Okay, how do I know it's two-sided? There's no plus or minus symbol. Okay. Oh, yeah, maybe I didn't. Okay. In case you never plan on getting the book, here's that. And here's that. Okay. Should I go with the others? Yeah. Okay. So quickly, page 138, homework for those of you that are never getting a book. Okay, so that's up to 13, 14. A little bit more. A little bit more. And then the next page, 139. I'm not sure we have to do any of these. We'll do it just in case. Okay. So here's the graph. Okay, where were we? So limit as x approaches 0. Negative infinity, two-sided. On both sides, they drop to negative infinity. D, limit as x approaches 2 from the left. We're approaching 2 only coming from the left side, and the y values drop to negative infinity. E, limit as x approaches 2 coming from the right side. Positive infinity. Okay, now they don't ask for it, but if they ask for the two-sided limit as x approaches 2, right? The two-sided limit does not exist because I don't get the same answer coming from the left as coming from the right. Okay, if I came from the left, we were going to negative infinity. If I came from the right, we go to positive infinity. So if they ask for the two-sided limit, you just put D and E does not exist. All right, then F asks for the equation of the asymptotes. That means horizontal and vertical. Okay, so horizontal asymptotes, y equals 2. You have to say y equals. That indicates that it's a horizontal line. And we had y equals negative 1. Okay, so horizontal asymptotes, y equals 2, y equals negative 1. Vertical asymptotes, x equals 0, x equals 2. Okay. So there we go. All right, now here, 5 through 10, make up a graph that satisfies all these conditions. Okay? So you invent a graph, you make a graph that does all the following. Okay. The limit as x approaches 2 is infinity. All right. So see if I can do this without doing a common partner. As x approaches 2, it's two-sided. On both sides, they shoot up to infinity. Try to hold it like this. Limit as x approaches -2 from the right of the function is infinity. So as I approach -2 coming from the right side, it shoots up to infinity. The limit as x approaches -2 coming from the left side is -infinity. So as I approach -2 from the left side, I go down to -infinity. Okay, the limit as x approaches -infinity of the function is 0. So when x goes way out to the left, you approach 0. The limit as x approaches positive infinity is also 0. So I just made this go like that. And it says f of 0 is equal to 0. So I just put a dot there, and then I just kind of smooth it out. So there was a dot there, arrow there, arrow there. So I just connected the rest of it, and connected that, and connected that. Okay, so that's what we have for number 6. Okay, so I can try to read it again. Limit as x approaches 2 is infinity, both sides. If I approach -2 from the left, I go toward infinity. If I approach if I approach -2 from the right, it goes to infinity. As x approaches -2 from the left, we go down toward -infinity. If I go out to either negative or positive infinity, we approach 0. So if I go super far to the left, we approach 0. Super far to the right, we approach 0. And it says f of 0 is 0. That means it goes through the origin. And then just connect the rest of it. Okay, that's that one. Okay, number 8. The best thing to do for number 8 is, okay, pretend you don't see this. Just look at quadrants 1 and 4. Okay, now I can't hold that position, but just pretend you don't see anything here or here. Okay, I know it's kind of hard to do. But, okay, as x approaches infinity, limit as x approaches infinity of the function is 3. Okay, so we're getting real close to 3. The limit as x approaches 2 from the left is positive infinity. So as I approach 2 from the left, we go to positive infinity. If we approach 2 from the right side, coming from the right side, we drop to negative infinity. Okay. So right now, I approach 3 as x gets super big. On this side, I go to negative infinity, it says. On this side, I go to positive infinity. And then the last thing it says is that f is odd. You have an odd function. So if you have an odd function, you have symmetry with respect to the origin. So this thing will have a branch that comes down there. So there we go. And then this thing, if you reflect across the origin, okay, that means this was y equals 3, right? So the reflection would be y equals -3. So this becomes the asymptote on this side. Okay. This thing going way down here, the reflection across the origin would be way up here. A point way out here close to 3. If I reflect across the origin, it would be a point way out here close to -3. All right, so that's the picture for 8. Okay, so in summary, when x gets super big, y is close to 3. As I approach 2 from the right, we drop to negative infinity. As I approach 2 coming from the left, we go to positive infinity. And then it said it was an odd function. So I take the mirror image, cover this up. Okay. I reflect all of this across the origin. Right, so this thing bounces over to here. This thing would end up being this thing. Okay. So that's that one. Okay, and then 10. Okay, limit as x approaches 3 of the function is negative infinity. Okay, I don't know if you can see it. I can barely see it now. But there's no plus or minus sign, so this is two-sided, double-sided. Limit as x approaches infinity of f of x is 2, f of 0 is 0, and f is even. Okay, so once again, I'm going to try to, I can't do it. Cover this side here. When x approaches 3, both sides, we drop to negative infinity. When x gets super big, x goes to infinity, we approach 2. So there it is. And f of 0 equals 0. Okay, so we have this. F of 0 is 0. When I approach 3 from either the left or the right side, we drop down to negative infinity. When x goes to infinity, that means you plug in 1,000, a million, a billion, a trillion, you get real close to 2. And then it says we have an even function. Even functions have symmetry with respect to the y-axis. Okay. So I bounce all of this whole thing off of the y-axis, and we end up with this. So there's the entire graph now. Okay, so that's how you do those problems. Okay, so that's that. What time is it? 10:02. Okay, so I'll start some of the 15 to 37 on the next page. Find the limit or show that it does not exist. Okay, so there's a certain technique to do a lot of these problems. Limit as x approaches infinity. So what do I do if there's a fraction, right? Okay. Later on, we're going to learn a nice shortcut, but that's not until chapter 4, maybe even. But so we're not supposed to know it now. So that's another thing. If you know the shortcut, okay, I'll just say for those of you who've had calculus, it's something called L'Hopital's rule. Okay, and you say, huh? What are you talking about? If you don't know what I'm talking about, that's what I want. I don't want you to know it. But if you've heard of something called L'Hopital's rule, Fasano knows what it is. Okay, you can't use it right now either. You cannot use L'Hopital's rule, whatever that means. So you have to do what I'm showing you. Okay, so a lot of these problems have fractions. How do you do that? Okay, so 15. The limit as x approaches infinity of 3x minus 2 over 2x plus 1. Okay, again, ignore any dates here, although it looks like this happens to be the same date, but whatever. Okay, this is something that's sometimes called infinity over infinity. Okay, you say, what's infinity over infinity? Don't know. It might be infinity, it might be 0, it might be negative infinity, it might be 5. Okay? But limit as x approaches infinity. So if I plug in super big numbers, 1,000, a million, a billion, a trillion, the top is super big, right? The bottom is also super big. So I have a big divided by big, and I can't determine anything just by that. Okay, so what you do is a little algebra trick. Okay? Now, this is first degree. This is also first degree, right? Degree is 1, degree is 1. Okay? If they're both degree 1, the trick is to divide the top and the bottom by x. So here's what you do. Limit as x approaches infinity. Okay, ignore the red. If you ignore the red, that's the same as the original, right? And all the other funny lines. The limit as x approaches infinity of 3x minus 2 over 2x plus 1. Now you divide top and bottom by x, which is legitimate. I'm really multiplying by 1 in the form of 1 over x divided by 1 over x. Okay, so this is a legitimate step. I get an equivalent expression. And by the way, you have to make sure you're not dividing by 0. Am I dividing by 0? No, I'm nowhere near 0. I got super big numbers. Right? I'm plugging in a million, a billion, a trillion. Okay. Now you actually do the division. That's what I mean by these lines here. So what is 3x divided by x? 3 minus 2 over x is just 2 over x. Divided by, what is 2x over x? 2. Plus 1 over x is just 1 over x. Okay. So now I have the limit as x approaches infinity of 3 minus 2 over x divided by 2 plus 1 over x. Okay. And now here's where you want to know this. You should not plug in numbers. You should not say to yourself, oh, I'm going to plug in 1,000, a million, a billion. No, you should just look at this and say 2 over x. If x is super big, the limit is 0. Okay. I mean, getting very fundamental, you have 2 pizzas, right? You have 2 pizzas and a million people. How much pizza does everybody get? Everybody practically gets 0, right? You can't feed a million people with 2 pizzas. That's 0. Same thing with this, 1 over x. As x gets bigger and bigger and bigger, this expression is 0, right? 1 pizza, a billion people, everybody gets nothing. Okay, so anyway, 3 minus 0 divided by 2 plus 0, 3 over 2 is the answer. So that's the technique I want you to do for these kind of problems. Yes, in retrospect, so I'll teach you this, but you cannot use this as a shortcut. But yes, in retrospect, you're kind of saying, you only look at the 3 and the 2. When x gets super, super, super big, this negative 2 and that plus 1 drops into insignificance, where you would essentially just say, okay, it's 3 over 2. Okay. Or by analogy, suppose I said a billion. 3 billion, take away 2. That's essentially 3 billion, right? Suppose someone's a billionaire. Anybody out there is a billionaire? Okay, I'm not a billionaire. Okay, somebody has $3 billion. Oh, you lose $2. You want to? That's not. You basically still have $3 billion, right? The minus 2 means nothing at that stage. Or 2 billion. Oh, plus 1. I got $1 more. Okay, 2 billion and 1. You basically have $2 billion, right? When you have that much money, minus 2 or plus 1 is essentially nothing. Okay. Now, for you and me that don't have a whole lot of money, maybe that minus 2 or that plus 1 is a big deal, right? Okay. But if you're a billionaire, minus 2 and plus 1 is like, chump change. I don't care if I only lose $1 or gain $2 or whatever, right? So yeah, essentially you're saying it's 3 over 2, 3 halves. So yes, you can do that. So what you can say is I'm expecting the answer to be 3 halves. But what do you show me on a quiz or test or homework? You show me this process right here. Okay, here's another one. 19. Okay, limit as t approaches infinity, radical t plus t squared over 2t minus t squared. Okay, again, something quick and dirty. The dominating exponent is the 2, right? These drop into insignificance after a while. Oh yeah, it's a square root of t and a 2t, but they do not grow as fast as t squared. So if you want something quick and dirty, I would sort of cover these up because these are insignificant compared to t squared. And then you say to yourself, what's t squared over negative t squared? Oh, negative 1. So I'm expecting the answer to be negative 1. Okay. By the way, you might say, doesn't t get big and square root of t get big? Yes, but not compared to t squared. Okay. Suppose I plug in a billion. You might say 2 billion, that's big, but a billion squared is way bigger. A billion squared looks down at 2 billion and says, you're a really small number. That's, right? I mean, it's just like saying the difference between a billion and 2, right? If you have $1 billion and you have $2, I mean, that's a big difference. That's the difference between a billion squared and 2 billion, essentially. Okay. Well, in any event, okay, this is like second degree, although it's not really a polynomial, but its dominating exponent is 2, and the dominating exponent here is 2. So this time the trick is to divide top and bottom by t squared. So notice what I did over here. What time is it? Okay. So I have in red, that's the original, divide top and bottom by t squared. And then I do the algebra. Okay. That divided by that, okay, that's like t to the half, right? T to the half divided by t squared, that's t to the negative 3 halves, or 1 over t to the positive 3 halves. Okay, you can do the algebra, it's 1 over t to the 3 halves. Okay, again, this is t to the 1 half over t squared. You would subtract 1 half minus 2 is t to the negative 3 halves. There it is. Okay. Then I divide this. What's t squared over t squared? 1. 2t over t squared, that's 2 over t. Negative t squared divided by positive t squared, negative 1. Okay, and here's the big thing again. That and that both approach 0. So when it looks like I'm crossing it off with an arrow, it means they're going to 0. Okay, 1 over t to the 3 halves, that approaches 0 when you plug in big numbers. A million, a billion, a trillion, 1 over that's going to be 0. Likewise, this approaches 0. 2 over a million, 2 over a billion, that approaches 0. So you have 0 plus 1 over 0 minus 1, which is negative 1. So final answer is negative 1. And please notice, keep writing limit, lim, until your final answer, you don't write limit anymore. Here you, quote unquote, plug in infinity. I mean, infinity is not a number, but you're plugging in bigger and bigger and bigger numbers. That's the idea here. Okay. All right, so I'm going to stop there. I'll pick up from here tomorrow. We're just about out of time. Stop the share. Check something on the chat. Okay. And yes, you're always allowed to chat, and if a persona, if you feel like you can always chat there. If the line has a closed or open dot on it, is it continuous? It depends. Okay, so, well, I have to share with me, well, okay. In order for the graph to be continuous, it has to be continuous on both sides. Once you have a jump, then it would no longer be continuous. Okay, and let's see, and if there's a hole or a jump, the function is not continuous, correct. Okay, and that's the, yeah, okay, yeah, that's fine, persona. We go with that. Okay, and I think that'll do it for today. I don't have time for anything else, so that'll do it for today. All right, so folks, I'll continue with this. Tomorrow's Friday, so I'll stop at, I don't know, 35 or 40, and then I'll give you the quiz, and I'll put you in your breakout rooms as usual, and then you can work in your breakout rooms, and the quiz is not due until Monday, so you can do the whole weekend on it. So when class starts again on Monday, that's when the quiz is due. All right? All right, folks, so that'll do it for today. So have a good day, and we'll see you tomorrow. Okay, bye,
Thank you,
everyone.
Professor. Take care.
Thank you,
Thank
Professor.
Thank you.